Okay, so if you recall, the last lecture was very much modern physics. This lecture is also very much modern physics. It has a, end of the freshman sequence quality to it. The reason being, I'm, constructing a, writing a story, and I wanted to say the whole story. And you may have seen portions of it in the past, but that's okay, I want to include it. So today is another such lecture. I hope to go through it very quickly so we can move on. Basically, between today, maybe another day, I'll prove things like E equals mc squared, very much a modern physics topic, but it has to be covered. I just want to put, make this sort of a complete story. That's why I'm including it. Towards the end of this chapter, towards the end of the section, before we move into tensors, there's a few problems on binding energy and so on and so forth. I literally copied them from some of the freshman textbooks out there. I won't be covering them in class. You use momentum and energy conservation. I'll do one sample problem, and you just figure out the rest. I'm not going to discuss that, nor am I going to test you on that. That is just a conservation of energy, conservation of momentum problem. We want to move on. We want to move on to tensor calculus, talk about field theory, and then get on to gravity. Okay, so again, as promised, a little bit of modern physics. I don't know where I got this notation from, particularly when I talk about force, but so little p is going to be the momentum you're familiar with, so I'll use a big P. For momentum is exactly what you would expect, m times mass times the 4 velocity. Mass times velocity is momentum. But this time we use proper 4 velocity. So what is this? Gamma c gamma u. Okay, and well, I can take this inside, but look, when I do. I'm calling this guy P. There's a little bit of content here. So this little p is not mass times the ordinary free velocity, but now you might say, well, I had a choice of calling it m times u or m times gamma u. Why did I absorb the gamma? Here I just explicitly wrote the gamma. It's m because when I did, you see these two here. So here I wrote the gamma, here I didn't. Whatever is on that side, I called it momentum. There's a reason for it. For us, it works out. It's a consistent definition. Things will go smoothly. But there's a little bit of physics you need to consider. The question is, when net force is zero, net force typically is zero because for every action there's an equal and opposite reaction. So when you add up all the forces on all the objects that are interacting, the net force is zero. What we want, because of net force, how is momentum defined, by the way?
It's the derivative. It's the integral of force.
It's a rate of change of momentum.
Yeah, that's force.
So if force is rate of change of momentum, so if net force is zero, the net rate of change of momentum is zero. What that means, that translates to the net momentum is a constant. It turns out from doing particle fundamental physics experiments, what is actually conserved, what is actually constant is this guy, and it includes the gamma. That is the reason why we're including P, the gamma, in the definition of momentum. Okay? Also, there is an example in the, I can use that, I can add it onto the notes when I'm updating the final version of chapter 3. There's a book by Marion and Thornton in classical mechanics. I bet there are many books out there that talks about it, but they use an example to use symmetry to make it clear why gamma should be included in momentum. Okay? It's just a classical mechanics argument. I will include it in the notes, I think, I hope so, if I have it already written up. If not, read up, I'm sure the library has the book, Classical Mechanics by Marion and Thornton. It tells you why that should be the expression. It is not particularly a GR level topic. This too could be a modern physics kind of an argument. So please go through it. Like I said, if I have it written down, I can add it to the notes. Okay, so when we proceed, I want us to know what gamma looks like. Gamma, what is gamma? 1 over square root of 1 minus
V squared.
A squared. Now, I can Taylor expand this because very often we want to get to the non-relativistic case. Not every car is moving at the speed of light or near the speed of light, nor is a spaceship, right? So what we want is a useful expression for gamma when beta is very small, when V over C is very small. How do you do that? You keep the first 2-3 terms of the Taylor expansion. Taylor expansion is done around the point beta equals 0, where it's not moving. You know that already. When beta equals 0, gamma is clearly 1. You should verify this when you take the Taylor expansion. The next term you get is that. So this is the first relativistic correction. Verify this, okay? And this we won't ever need if you're trying to be very accurate. Turns out it is beta to the 4th. Of course, it's an infinite series. We'll usually this is Newtonian. This is the first relativistic correction. That's where we'll typically start. Okay. Then we have seen u equals minus c squared. Correct? Therefore, what is PP? You tell me.
Just be MC squared.
I realized what I just said.
Yeah.
I tried to hold it.
It'll just be MC
All right, well.
negative MC squared.
Good. Well, not MC squared.
U squared.
M squared C squared.
M squared C squared.
Yeah, there are 2 M's. I'm not going to say there are 2 P's anymore, but 2 M's.
You already made the mistake. Might as well look.
You need to
Own it?
Yeah.
Yeah, right.
All right.
Just say P and SMO.
No.
FYI,
Camera.
I'm teaching a bunch of 10-year-olds. All right. Are we good?
You're the one who said PP.
We're good.
Most of us are doing it.
So I'm going to define relativistic force. The 4 force, I'm going to use uppercase K. K, you guessed it. What do you think it is?
Oh no, DPD.
D tau. Okay? Just as before, you will have, recall, UA equals 0 in a similar way. Because they're just multiplied by. Because P also has constant length. So when you take the derivative of this, you get 0. Okay? Now, let me do the 3 force. recall all three vectors are bold-faced in my notes. 3 force is, no, before I will get to 3 force, sorry. I'm going to define this the spatial component of this guy, because we want to talk about force. Well, that's just d tau, and that's equal to dt d tau dp dt. But this guy is our relativistic force. Okay? The spatial component of the 4 force is gamma times 3 force. Again, this is the one that satisfies Newton's third law. The net force is 0 for every action. There's an equal and opposite reaction. As a result, it is this P that is conserved, or equivalently, this guy that is conserved. Yes, Jackson?
You're calling the spatial component of the 4 force little k? Is that what that is?
The bold K. Yeah.
Okay.
So yeah, let me be.
Gotcha, yeah.
This is also, there are no little K's here.
Yeah, sorry, this big k.
Yeah. Font and boldface becomes difficult. So. Okay, so what will that get us? First of all, let's do this and do a simple problem to see how mechanics becomes very interesting and very, not difficult, it's just a little bit of a hassle. Simple mechanics problem. If somebody is accelerating with a jetpack, or with precisely g, let's say in space, what is the equation of motion? Well, x equals x0 plus v0t plus 1/2 gt squared. Right? We're going to find that. That is the simplest problem you can do. So let's do that, except let's do that in a relativistic setting. Because that observer has a proper time that moves in a different rate with the inertial observer. So this is example, I think, 3.8. So this is far away in space. So you have, I don't even want to put vertically, you have one x dimension. And in this x dimension, the observer is accelerating with constant g, starting from rest. So u0 equals 0. And let's see what kind of motion prevails. Okay? So whenever I talk about u, I only have u0 and u1. Time and x coordinate. There's no y and z coordinate. I mean, it is. It's constant. You know. Yeah.
Capital.
Yes. Yeah. Please, I think bear with me for 1 or 2 more days, and then we're done with this 3-dimensional stuff. Okay, so what we'll do is x component of velocity, that's the only component of velocity that exists. And this is velocity with respect to regular time, observer time. So ux okay. This gamma comes in here because really hidden in here is the derivative with respect to proper time. But the interesting part, this is no longer proper time. This is just the coordinate time, as I've clarified over there. So this is the acceleration, or mass times acceleration, so it is mg. Force equals mg. Ooh. Let me do it this way. It's not equal to, this is a vector. Those I just make the x component of it. So then I can write du1 d tau is equal to, what is it? Gamma du d tau. Is that right? No. I think so.
But mass would still be there, wouldn't it? Wait,
Hold on.
sorry, D1.
Yeah.
D1.
Equals dt tau dt gamma x equal to, this guy is g. Agreed? This guy is u0 over c. It is only confusing because we have to keep track of so many things in mind. C gamma 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 is dt d tau. This equation, we will need it. It's not a very important equation, but it's just for this problem. But we'll refer to this equation. And good. This is what I wanted. That worked out. And so, tell me where I get this from. Well, this is by definition where did I get, I mean, this is just definition. du0 d tau is the zeroth component of acceleration. Where did I get this from? Why did this equal that? Don't overthink it. The answer is on the board, same side of the board. The line that I didn't erase.
Is it because of the eta function right there?
Line B equal to cancel.
So u and a is perpendicular. Both u and a only has
All
zero.
components will be
zero.
perpendicular. Oh, well, look, because there's only x here.
There's only
Because there's
only x
It
component.
has to be equal to the time component.
Correct.
Yeah.
Yeah. It has to be equal to the time component, and it has to be greater than zero.
Yeah.
I mean, because everything is moving to plus. Okay, now I'm going to use this and write this as du1 d tau, and hopefully I've done this. So that's equal to u1 g over c u0. And therefore, I get the second equation that we need. Our work is really over. It just seems very abstract. And it doesn't seem like we're doing a simple acceleration problem. So let me copy these two equations. just going to leave it there. We can use that, but any questions? This comes from, well, this is just definition. This comes from the fact that this is 0. But then I have U1 over here. A1 is U1 over, du1, d tau. And this one, I took the previous value and set it in. Very counterintuitive. We don't know what, not counterintuitive. You're almost going, I don't know what we're doing here. Yeah? Fine. Just give me till the end of the problem. But you're saying, well, I follow the steps. We'll see where we're headed, and then when you backtrack, it can make sense. Okay, and so I'm going to take this derivative one more time. So then I get d squared. You can almost see where we're going. Tau squared is equal to g over c du0 d tau, but then I'm going to use this equation. So I'll write it below and you will see. So g squared over c squared, yeah. Agree? I'm going to replace this with that. I know how to solve this. If this was a negative sign over here, if there was a negative sign over here, what's the solution to this?
A sine function.
Cosine and sine.
Cosine or sine.
If you don't have a negative sign, what's the solution to it?
It's exponential.
It is cosh and sinh.
Oh.
Yeah. But what's the second derivative of cosh? What's the first derivative of cosh? Sinh. Yeah. What's the derivative of sinh? Cosh. So it comes back to it. Yeah. So you can easily check your handbook of special functions and find that this is true by calling this some a sinh g over c tau plus b cosh g over c tau. Why do I have g over c? Every time I take a tau derivative, g over c comes out. And I'm taking two derivatives, so obviously g squared over c squared comes out.
So, why can't we just use an exponential function here?
We can, but it works out beautifully here. Exponential function, yeah, e to the x, e to the minus x. That is what sinh and cosh is made of. Cosine and sine is made of e to the ix, e to the minus ix.
Yeah.
Yeah, but if I write sine and cosine, you won't say, well, why didn't we use e to the ix and e to the minus I? This is just more handy. Okay, now initial conditions. So we have practically solved the x component of velocity. That's what this is. Well, let's make it physically real. I'd like to, at the end of the day, I'd like x equals something, t equals something. Okay, that's what I want to see. So let's put some initial conditions. Initial condition. What's a good initial condition? At tau equals 0, the object is starting from rest, which implies u1 equals 0. So which of the two goes to 0? I'll give you a hint. Sinh of 0 is 0, cosh of 0 is 1. So either A or B goes to 0. Which one is it?
A has to go to 0. Oh, B has to go to 0 so that T, so that tau is 0.
Correct. So immediately we get u1 of tau equals some constant. Oh, I should have mentioned, A and B are what?
They are 4 vectors.
No, sorry. I should have clarified. these guys. Some numbers. Yeah, depending on the initial condition. In particular, this requires that B equals 0. So notice, since this is 0, gamma 0 is 1. Because gamma is 1 over square root of 1 minus beta squared. If u is 0, beta is 0. So gamma is 1. Initial gamma is 1. Okay? So therefore, I can write, I need to know this condition. du1 d tau, evaluated at tau equals 0. Well, by this equation, it is g over c u0 of 0, but that's equal to g over c. u0 is nothing more than c dt d tau, evaluated at 0. The c's will cancel. This is gamma 0, and that's 1. So I would get du1 d tau of 0 equals g. This will enable me to calculate what A is. Let me do du1 d tau. A times G over C cosh G over C tau. This implies du1 d tau evaluated at 0 should be A times G over C, and that has to end up being G from above. How can that happen? That can happen when A equals what?
C.
Yeah. This to happen, we need A equals C. Totally unintuitive problem, but it would appear that we have fixed. We'll bring reason and sanity to this problem. It's so difficult. It's like I don't know why we do any of these things. If I know u1, can I solve for u0?
Take the derivative, right?
Yeah, take the well, to get u0, I would take the integral.
Oh, and you could do the top part.
Or you could take the top part and stick it in there. But when you do, you would get u0 of tau equals c cosh G over C tau.
Just comes out to be exactly.
Yeah, because the derivative of sinh is cosh. And one of the g's goes away. There's a g over c over here.
Oh, well, I missed the fact that there's, yeah, I'm just paying attention to the function.
Yeah, so it just goes away. And when you solve it to the other side, it's g over c, you have c over g, so that goes away completely. You get these nice expressions. Okay, so then, now I want to find what t is equal to, and I'll write down what x is equal to. You'll verify this. So this this is c times dt d tau equals c cosh g over c tau. Well, that's simple enough. C's would cancel. T is the integral of cosh, which is sinh, but I would get what?
You get.
No, actually, I want CT because that's the usual pairing.
Okay.
CT.
So you'll just get G, or yeah, G.
I would get C squared over G, because when you take the integral, it goes to the bottom. When you take the derivative, the factor comes out. So I would get. Does that make sense, guys?
Yeah, I see.
This is assuming the following initial condition. What's the initial condition?
That the U equals 0, U initially.
No. The time also starts at 0.
Proper time, right? Oh,
No.
if
The
proper
coordinate time at proper time equals 0 is 0.
Yeah.
So the integration constant goes away.
So that's not always assumed.
I mean, I can choose to start the problem at coordinate time equals, satellite rocket launch at 7 p.m.
But you would normally want to say that the coordinate time is equal to 0 whenever the proper time is equal to 0. Right? Because that makes everything easier.
Correct. But that's not.
That's not how the world works.
No. I mean, but I have to state that.
Oh, okay.
Yeah. So in Central Time, it's 0. But Pacific Time, it may not be. So, I mean, otherwise it's no big deal. I just get a constant over here. Here's the interesting part, and this is what I'll let you do it. When you do this for x, only because we want things to work out nicely. What do I get for x? Yeah, I get this. C squared over G, well that's nice. Cosh G over C tau, with the understanding that x. Listen, what do you want to say over here?
You want to say 0.
Yeah, I want to say 0, but we won't. This works out so nicely because cosh of 0 is 1.
Let's see.
Otherwise, no.
So if you say 0 for that, you will get an extra constant on the outside.
Yeah. There's a reason why I want the constants on both of those to go to 0, just so that I know how to graph a nicely centered parabola. Otherwise, I don't know how to graph.
It just makes things look prettier.
It just makes things look prettier to draw.
The constant would
If I were drawing, which I'm not.
the constant would just be negative C squared over G. wouldn't it?
You can put any constant plus some x0.
Wait. But wouldn't the constant, if t was equal to 0, if at proper time equals 0,
Yeah.
x equals 0.
Yeah, it would be minus c squared over g.
Minus C squared over G.
Yeah. I'm just pushing everything away to. So then the reason being, I know one formula. Well, I don't really know it. I just had to look at it because I don't know which way the minus sign goes. Sine squared theta plus cosine squared theta is 1. What's the equivalent sinh and cosh formula?
Say that one more time, sorry.
Sine squared theta plus cosine squared theta equals 1.
Yeah.
This is the trigonometric version of Pythagorean theorem. What is the equivalent hyperbolic formula? Cosh squared minus sinh squared equals 1.
Okay.
I don't know where the minus comes from, the sinh squared or cosh squared. But my handy dandy notes. So, it turns out it's cosh squared minus sinh squared, and therefore g over cx squared minus g over c squared. Oh, I wonder if that's a mistake. Oh, no, c squared. C squared. Yeah, this is typically how a hyperbola, not parabola, hyperbola. Looks like. So
That has to equal 1.
I should have graphed this ahead of time.
So x is greater than ct.
That sort of looks like a hyperbola, right? Let's see what hyperbolas look like. So please verify if that's the way it's going. So for us, we don't have this guy over here. We don't have this guy over here. This is the point. C squared over G. This is time. This is x.
X has to be greater than ct.
X has to be greater than ct.
Phase like.
Oh, so I don't know if it's this way. I don't know, but that's, I want to see that graph plotted, use maple and plot it. X has to be greater.
If x has to be greater than ct, doesn't that mean that
Yeah,
it's...
this looks right because it has to be time-like, right? So slope has to be always greater than 1. Maybe approaching 45 degrees. Yeah, this is the path taken by an observer with a jetpack. Seems somewhat reasonable. If this observer over here was not moving at all, that would be the path. But the observer is moving, so it has to go this way. Now the thing is, it could go this way, or it could go, I don't know, something. But just check, I think. I'm kind of curious. I would totally appreciate it when I walk into class on Friday, that's a graph of this. No, seriously.
Yeah.
David, you usually grace us with your artwork. How about gracing us with a graph on Friday?
Do you have maple?
You can deploy the full arsenal of your classmates.
I'll grab it.
Okay, I want to get started with MC squared.
Did you say for 100 bonus points?
No.
No, that's fine.
To incur no negative points in the next exam.
Oh, man. Jeez. If x is greater than ct, for some reason that sounds like it would be space-like.
No. X squared minus ct squared equals 1. Some weird set of units.
Well, x squared minus ct squared times g over c squared.
Well, let's graph. No. Oh. What is, verify that we can do that. What is u? U is u0, u1, right?
Mm-hmm.
Okay, let's do u squared. U, and that is minus u0 squared plus u1 squared.
Yep.
What is that? Minus, what is u0?
U0
C, I know there's a C.
c cos g over c.
Sorry, u0 squared, u1 squared. This is what?
Cosh.
Cosh.
Cosh squared.
Cosh squared. I don't care about,
G over c tau. Plus, then it'll be c sinh squared.
why am I doing this?
it's
I know
that.
the answer.
I see, it's equals c squared.
Minus
Minus c squared.
minus c squared.
Okay.
It is time-like.
Interesting.
Oh, good point. Good point, you guys. I should have graphed this, and I just don't want to do it on the board. But it's a very important lesson, and good that I'll task that to you guys. Let me see if I can cover anything more realistically. No, I want to take my time with relativistic energy. So next time, I'm going to, I hope I finish particle dynamics. There's a section called binding energy. Just a couple of problems really. I want you to solve that on your own, and then we move into tensors. And we'll wrap up, we'll do classical field theory, largely the time-Gordon field and the electromagnetic field, and then move on to gravity. We're not in a rush, but we need a good 1.5 semesters of gravity.
So next time we're going to get into like resonance energy and stuff like that?